Thank you for giving me a chance to talk in this wonderful workshop. I would like to talk about is orbit surfaces of the three-dimensional geometries. So what do you mean by the three-dimensional geometries? According to the Thurston's geometrical program, he suggested a kind of three-dimensional geometries. So the model space for the 8 geometries is first of all the space forms, which is R3 and S3 and H3, and next one is just homogeneous 3 manifold, and Sol is just a solvable 3-dimensional manifold. If you see this these models of 8 geometries, the first line, the space is this one has largest isometric group. The dimension of the isometric group of this space forms 6, and the second line has dimension 3 for the isometric group, dimension 4. And for the Sol, this is the only model space which has 3-dimensional isometric group. Okay, so what I'd like to do is that consider the isometric group of X on X. Now I'd like to find out one-dimensional closed subgroup, which I will call Xi, which acts on X freely and properly. Then if we mod out X by the action Xi, then we get the orbit space, which becomes two-dimensional manifold, that means surface, because of this condition properties. So if we have this kind of Xi, one-dimensional closed subgroup of the isometric group, then we can get Riemannian submersion. So now from this Riemannian submersion, we can think of the base manifold. This is the surface. I will call the orbit surface. So I'd like to have interest in the geometry of this orbit surface. So first of all, what I want is that to classify all the orbit surfaces up to isometry. Next one is to understand the no, because the action is free. There is no singularity, and the orbit surface is Hausdorff because of the properties. So the basic two things that I want to know about the orbit surface is the Gaussian curvature, and the next one is how to get the group of isometry of M by using the vibration as I saw you before. By using this vibration, I can calculate the some symmetry of the base orbit surface. Okay, so first to classify M, what I have to do is first we need to now find the one-dimensional subgroup Xi acting on X freely and properly. Next one is, by the way, here we have a very well-known lemma, which says a free action of a closed subgroup of isometric group is automatically proper. So we don't have to care about the properties. Just think of the free action of the one-dimensional group. The next lemma says that to classify the one-dimensional subgroup, it's enough to classify up to conjugacy. What I mean is that by this lemma, if there are two subgroups of isometric groups which is conjugate, then this element G, F, induces an isometry between the base orbit surfaces. So it's enough to classify up to conjugacy to get the one-dimensional subgroup. Hence, so I will use psi t because it looks very strange, but I will use this one instead of G or H or something like that. So I have to classify all the one-parameter subgroup of isometry up to conjugacy and up to parameterization. Now, if you see the H geometry, the model spaces of H geometry, most of them have a global trivialization. So we can get a coordinate system from X to R3. So the inverse map of this phi is the coordinate system. So this is, in most cases, it's a global coordinate system, except the sphere case. Okay, now by using this coordinate system, we can get a coordinate system for the orbit space, which is, okay, how can I get is that if you see the action of the psi to the x, then the coordinate two planes, like xy plane or xz plane, yields a global cross-section for the Riemannian submersion. So this part will give the coordinate for the base surface. So xy or xz or yz will be the coordinate system for the M. Okay, now how to get the Gaussian curvature of M? This is very easy to use some theorem. We have O'Neill's formula, which tells compare the curvature tensor between the base manifold and total manifold for the Riemannian submersion. If we apply this O'Neill's formula for our case, it becomes like this. The K is sectional curvature plus something like this. Oops. Oops. Okay, here K is the Gaussian curvature of the base surface, and sect VW is the sectional curvature, where when we calculate the sectional curvature, it's enough to calculate the horizontal frame for on X. This notation, nu means the normal part of this vector. So this is the Lie bracket, the normal component of the Lie bracket of VW. So once we use this this formula, then we can get the Gaussian curvature very easily. Now, how can we get the isometric subgroup of base orbit surface? So let's consider the normalizer of the one-dimensional subgroup psi, which acts on X in a way that it preserves the fiber. So and induces an action on M isometrically. Also, psi acts on M trivially, so that if we mod out M by psi, that becomes the isometric group of the base surface. So we will calculate. I calculated this M mod psi, the subgroup, which becomes the subgroup of the isometry group of the base surface. Okay, I will use this kind of notation. So I of X means the isometric group of X, and psi t is the one parameter subgroup of, oops, yeah, all right, the isometric group of the model space. And I explained what phi is, that will give the coordinate system. And when I use RT, this means the rotation. And R hat T is the three-dimensional rotation, which fixes the z-axis. And IN is just the n by n identity matrix. Okay, let's see each case of the 8-dimensional model space. So first of all, Euclidean space R3. Here, the coordinate system is just identity map. We know that the isometric group of R3 is semi-direct product of R3 and SO3. We can classify psi, then we get only two kind of psi's. The one is just the translation along the z-axis of the conjugacy. And the second one is a kind of screw motion. Okay, then the base surface, the orbit surface becomes, when psi t is the just translation, then the orbit surface is clearly a plane. So the Gaussian curvature is 0, and the orbit surface is flat. It's almost trivial. Now, how about the screw motion case? When psi t is this kind of screw motion, then the curvature has the Gaussian curvature looks like this, and the isometry group is SO2. So if you see this curvature function, you can guess SO2, this orbit surface will have the symmetry of SO2 because of this one, even though this is not necessary and sufficient condition. If you see this part, K is rotationally symmetric. Now let's see the next case, the spherical geometry, S3. In this case, in fact, there is nothing to do. First of all, the isometry group is SO4. We have a big theorem about this case. Gromov and Grove proved that there are the only free and proper action, one-dimensional action on SO3, which gives the Hopf vibration of the orthogonal congruence. So there is nothing to do. I mean, just there is only one action, S1 action, one-dimensional psi is S1, and the M, the base surface is just the sphere. So it's not interesting. How about the next case, the S2 cross R? So the isometric group is just the product of the isometric groups of each factor. There are two free actions on this case. One is the first one is just the translation along the jet factor. The second one is also I don't know how to I don't know whether if I call it screw motion or not, but anyway, this is the rotation and the rotation and the translation on the last component. Okay, now, so we have two kinds of M. For the first one, because for the first case, you may easily guess that M is just S2 because the action is translation along the z-axis. For the second case, the Gaussian curvature is like this, and here, if you see this part, K has the rotational symmetry. So you may guess the isometric group of M is SO2. I skip something. I skip H3, so I will do it at the end because it's very complicated. Okay, so next one is the H cross R. This is also kind of complicated. First of all, I will regard H cross R as the upper half plane times R. Before classifying psi t, I have to talk about the Iwasawa decomposition of SL2R, which is related to the isometric group of H2. Oops. I'm sorry, I'm not used to these toys. Okay, so what do I mean by the Iwasawa decomposition of SL2R? Any element of SL2R can be written as three parts. One is called the parabolic, the first part, and the second part is hyperbolic, and the third part is elliptic. So this is just a rotation. So any element in SL2R can be decomposed uniquely in this way. So there are four possible one-dimensional action for psi: trivial, parabolic, and hyperbolic, elliptic. So for the trivial case, just is translation on the R factor. Oops, this factor. So will be no interesting. Will have no interesting geometry. For the parabolic case, this is the translation to each direction. I mean, the H2 and to our direction. For the hyperbolic case, the jet part, for the H2 element, it has a scaling, and for the R part, it's just a translation. For the elliptic case, this is, I have to explain a little bit about this action. The action of psi on the element on GR is R, oops, this is large RT, rotation, times G, and the R factor is R plus CT. So what RT times G means that if we have SL2 elements, SL2 elements phi, then RT is so RT times G is just plug in G in here, so cosine T G minus sine P G, something like this. So this is called the linear fractional transformation in complex analysis. So the RT times RT acting on G is this action. Oops. Where is the M? I'm sorry, I lost one page. Okay, so for the trivial case, as you might guess, there is nothing interesting. It is just the M should be H2. And for the parabolic case, the curvature function is a little bit complicated, but one interesting thing is that when we see the when we use the coordinate for M by X and Y, the curvature doesn't have one variable. That means it has an R symmetry. So in this case, there is a one-dimensional symmetry for the base manifold, which is isomorphic to R. For the hyperbolic case, this is the same. Except one case. If C is 0, this is just H2. So that's not the hyperbolic, oh no, R2. Why? Yeah, if C is 0, then the base orbit surface is R2, flat R2. And if C is non-zero, then it has also, the base manifold has the one-dimensional symmetry too. For the elliptic case, hyperbolic. Oops. Yeah, it has the one-dimensional symmetry too. I'm sorry about the missing the one page. Okay, let's go to the next case, nil case. So nil is, if we use the 3x3 matrix, the group of nil is the set of this kind of elements. So the isometry group of nil is nil with the semi-direct product of nil and SO2, where SO2 can be regarded as automorphism of nil. So how to act on element of S2 on the nil? The action of SO2 element RT is acts on the element of nil as follows. So RT acts this, where the coordinate x prime, y prime, z prime becomes as follows. So if you see x prime and y prime, RT acts as a rotation exactly. But for the central direction z, it's quite complicated. So it looks like this. So then the pair A and RT of nil and SO2 element acts on the element of nil of this way. So first of all, act on RT on X, and next multiply this with A. That's the action of this element, the nil semi-direct product of nil and SO2. Okay, there are three cases for possible psi t. So if you see this, oops, I'm sorry, this is misprint. Yeah, this one should be changed. This part is 0 and z is t, and this is 0 and this is 0. So t is, for the first case, t is sit on the central direction. For the second c, the parameter t lies on the x direction. And for the third one, this is, this part should change to here. So central direction with some constant multiplication c. Okay, now let's see the geometry of M. For the first case, the base surface is flat R2. And the second case, the curvature function becomes like, Gaussian curvature becomes like this. So here there is no jet appeared here. that means it has a one-dimensional symmetry. So especially in G direction, it has a symmetry. So the isometric group of the base manifold is of this form. So translation in the central direction, that gives the isometric group. For the third case, the curvature function is very complicated. But if you see here is R's, where R is the square root of x squared plus y squared. So you can imagine SO2 action is the isometry of the base manifold. Okay, for the PSR, the universal cover of PS2R case is very quite complicated. Let's see first. SL2R. If we have an SL2R, by the Iwasawa decomposition, we can decompose every element of this form. Then the isometric group PS2R is PS2R cross K, where K is the rotational part, this part, compact part, which acts on. So this part is just the left translation. This action, the action of this part is just left translation, and the action of this part acts on the right translation. Now let's take the universal cover of this setting. Then the isometric group of the PSL2R tilde is PS2R tilde times K tilde mod G, where G is the center of this universal group. Now let's see this one again. We call this kind of one-dimensional group parabolic. For this one, hyperbolic, and this one, elliptic. So keeping that in mind, let's see the action of psi. There are four kinds of actions. So the first one is trivial. That means for the first part, the PS2R part, it acts like identity map, and for the K part, it acts on the rotation. That means act on X by right rotation multiplication of this amount. For the parabolic case, psi t looks like this. This is just the how can I say it? Okay, let's see next case, then we can understand easily. Okay, so anyway, there are four kinds of actions, possible actions for psi. So when I have 2 minutes more. Okay, so the geometry of N is as follows. For the trivial case, we have the hyperbolic two plane, and for the parabolic action case, K becomes very messy. So the base manifold is not so good. But when C is 0, then this becomes just 0. So M is R2, the flat surface. Anyway, if you see this Gaussian curvature, there is no jet involved here. So you can imagine isometric group has one-dimensional symmetry. For the hyperbolic case, much more complicated. And for the elliptic case, we exclude the C equal to one case, because in this case seems to be very natural. What I'm saying is that when C is equal to -1, then the element acts on the X by conjugation. But we should exclude this because in this case, when C is equal to -1, we cannot get the free action. So, and in elliptic case, the K is terribly, terribly complicated, as you see here. But anyway, there is one-dimensional symmetry. Okay, let's see Seoul case. Seoul is, solvable group is, in terms of the matrix notation, Seoul is the set of this kind of elements. Okay, so there are two kinds of free action. So the first one is, this is 0. This is X is 0. So that is sort of diagonal action. And the second one is just off diagonal action. This is 1, 1. So in this case, if we see the base surface, the curvature function looks like this. But this case is very interesting because the isometric group of the base surface has zero-dimensional. So this is the only case that which has the zero-dimensional isometric group. And for the second case, it has the one-dimensional symmetry too. Okay, for the hyperbolic space case, there are many ways to model the hyperbolic space, but I will use this kind of model. Use the quaternion. So the element of the hyperbolic space can be expressed as quaternion, where the k part is, Q has no k part, and the j part has the positive number. Then the isometric group of H3 is PS2C, where the action is given by kind of linear fractional action. We can't use the linear fractional transformation in complex analysis because the quaternion is not the multiplication of the quaternion is not commutative. Then three kinds of psi happens: elliptic, parabolic, and loxodramic. So that corresponds to this kind of things. So this looks like the same as the elliptic case in PSL2R case because this is a rotation. And for this one is parabolic as the same as in the PSL2R case. And for the loxodramy case, I don't understand why this is called loxodramy. But anyway, this is well known that there are only this kind of one-dimensional subgroup. Okay, so for the geometry of M, the first case, there is no elliptic free action, so that in this case, the parabolic case, we can get any surface. And for the elliptic case, we can get a surface. For the parabolic case, we get the two-dimensional hyperbolic space. For the loxodramy case, the curvature function is very complicated, which is, and it has also the SO3 symmetry. So up to here, so I tried to get all the possible two-dimensional surface given by out of the 8-dimensional geometry using the one-dimensional closed subgroup. Okay, that's what I thought.
Questions or comments?